Thank you for the introduction. I am Giorgio Cora, a PhD student from Politecnico di Torino, and today I'm going to present our research work related to the enhancement of RISC-V-based ecosystem for SEU-Resilient inference on FPGA implementation. So, as we have seen between yesterday and today, the many more fields are adopting RISC-V coupled with AI accelerators in their platforms, and these obviously include also the space one. However, when safety critical application comes into consideration, then what we have to consider is obviously not only performances but also reliability, as we have seen. And the main drawback of the traditional approaches, as we have seen, is that we maybe pay a lot in terms of system availability time, especially during to perform either error detection and, most importantly, error correction. So our idea was to propose a custom platform that is able to increase as much as possible the system availability time, even when errors affect the actual behavior of the system. And we try to do so and to achieve so by also reducing and minimizing as much as possible the impact of reliability methodologies on the actual amount of hardware that is being used. So this will be the actual outline for this brief presentation, and I will immediately enter into details about the actual platform. So this is the actual architecture that we implemented onto FPGA, and it is composed by three main components. The first one being obviously the RISC-V architecture, which is in charge of managing the entire system, of communicating and instructing the accelerators on the instruction that it has to execute through AXE interface, and also to manage all the error correction part. Okay. This RISC-V architecture has also been implemented in a TMR way and also isolation to further improve the reliability of the main controlling architecture of the entire system. Then, for what concerns the part of error correction, we implemented the DFX controller, which is in charge of performing partial reconfiguration of the accelerator when errors are detected. This will obviously help to introduce a fast and efficient error correction methodology. Finally, the third component is obviously the accelerators. In this case, we adopted a custom version of the tensor processing unit, which resembles the Google's TPU architecture, and this particular component has been modified to support error detection. So entering into further details about the actual accelerator itself and the error detection part, we know that custom and common systolic array architectures are based on 2D matrices of multiply and accumulate units. And when reliability features are implemented, some of the main drawbacks of such techniques are, for example, the amount of hardware that is required to actually perform the error detection, and also often that there is a lack of runtime testing, so the actual flow has to be interrupted to perform error detection. And the idea was to implement a custom error detection mechanism based on checksum to actually perform a runtime error detection. How we can achieve so? Both we initially obviously modified the actual instruction set architecture of the TPU itself, and so that we have a normal and a testing mode. And in both modes, obviously the flow is the same, so the flow of instruction is the same, so a load weight operation is followed by a matrix multiply operation. What changes is what is actually performed when the testing mode is active, because when testing mode is when the TPU operates in testing mode, what actually happens is that while the normal operation are being carried out, the checksum is also computed exploiting SIMD operation and using the bits in the DSP that are not used for the actual computation. And through this approach, we are able to compute the checksum and to compare their values with golden ones, still computed by the TPU themselves, and this can be achieved with a maximum overhead of 3 clock cycles per instruction executed in testing mode. So to actually evaluate the system, we implemented the platform onto a Xilinx KCU105 development board. Here you can also see the actual resource utilization of the platform itself, and as benchmarks, we adopted a CIFAR10 and NIST dataset. So for what concerns the actual results analysis, we have divided this into two parts. On one side, we analyze the actual error detection performances of the TPU, and then also the actual time required and time overhead to perform error correction. As we can see from TPU point of view, we are able to detect up to 90% of the fault injected inside the TPU data path, the systolic array data path, and from a time overhead point of view, as we've seen before, just 3 clock cycle for every testing instruction leading to a maximum of 0.64% overhead in the overall execution time when all instructions are executed in testing mode. For what concerns the actual performances of the platform, so the actual recovery times, obviously the actual reconfiguration time depends on the size of the TPU, and it is it's scaled linearly with the TPU size. And if we consider the amount of time that is required to resume the operation, obviously this is much better in the case of the DPRs. We do not have to re-execute all the previous layer. So a comparison with the case in which the full reconfiguration is adopted has been reported here. So to summarize and conclude, we proposed a custom platform that is able to perform both error detection and error correction inside the system in an autonomous way by exploiting both RISC-V architecture to manage the entire system and the reconfiguration part, and the systolic array to perform detection and efficient AI computation. And this is it for the presentation, and thank you everyone.